Welcome to Discrete Mathematics. Today, we are going to explore a fascinating and fundamental concept called sublattices. We will learn how certain smaller groups within a larger mathematical structure can perfectly preserve the rules of the original system, acting entirely on their own without needing outside help. By the end of this lesson, you will understand exactly what makes a subset self-sufficient. To begin, imagine a large corporate office with many employees. In this office, any two employees share a lowest common manager and a highest shared subordinate. Now imagine we select the IT team to form a smaller group. If any two IT workers share a manager and a subordinate who are also inside the IT team, the team is completely self-sufficient. However, if their shared manager is in the HR department, they must look outside their group. In mathematics, a sublattice is exactly like that self-sufficient IT team. Now that we have an intuitive picture, let us define this formally. Remember that a lattice is a mathematical set equipped with two operations: the meet, which finds the greatest lower bound, and the join, which finds the least upper bound. A non-empty subset of a lattice is called a sublattice if it is closed under both of these original operations. Being closed simply means that if you take any two elements from your smaller subset and apply the meet or join operation, the resulting answer must also live inside that exact same smaller subset. This brings us to the mathematical conditions, starting with the meet operation. Conceptually, this formula ensures that our subset does not break when we look for the greatest lower bound. The formula states that if element A is in the subset S and element B is in the subset S, then their meet must also be found inside S. The symbol S represents our smaller subset, while A and B are any two elements we pick from it. The wedge symbol represents the meet operation. If you increase the subset size, this rule must still hold true for every possible pair. Having established the meet condition, we must also satisfy the join condition. This formula defines the exact same requirement but for the least upper bound. It dictates that taking any two elements A and B from the subset S and combining them using the join operation, represented by the V symbol, must result in an element that is also safely contained within S. For a subset to officially earn the title of a sublattice, both this join condition and the previous meet condition must be satisfied simultaneously. If even one calculation points outside, the subset fails. Before we move on, let us see this with a concrete example to build confidence. Suppose our main lattice is the power set of the numbers 1, 2, and 3. This means it contains all possible combinations of these numbers. Here, the meet operation is set intersection, finding what two sets have in common. The join operation is set union, combining all elements. We are given a smaller subset S containing the empty set, the set 1, the set 2, and the set 1, 2. We need to determine if this is a valid sublattice by testing pairs. Now that we have our subset, let us test the meet operation for the elements containing 1 and 2. We calculate their intersection. Since a set containing only 1 and a set containing only 2 share no numbers in common, their intersection is the empty set. We now look back at our subset S and ask, is the empty set one of the elements listed? Yes, it is. Because the result exists inside our subset, the meet condition is perfectly satisfied for this specific pair. We must now check the join operation. Following the meet test, we apply the join operation to the exact same pair. We combine the contents of both sets using the union operation, which gives us a new set containing both 1 and 2. We look at our subset S again and ask, is the set 1, 2 listed there? Yes, it is. If we continue this process and test every other possible pair in S, we will find that every single intersection and union results in an answer already inside S. Physically, this means our subset is completely self-contained. Having seen a successful case, let us look at a slightly more complex example where things do not work out perfectly. Suppose our main lattice consists of all the positive divisors of the number 30. In this lattice, the meet operation is finding the greatest common divisor and the join operation is finding the least common multiple. We are given a subset S containing only 4 numbers 1, 2, 3, and 30. We need to find out if this subset is a sublattice. We will pick the numbers 2 and 3 to test. With our new subset defined, we first calculate the meet for the numbers 2 and 3. We know the meet operation here is the greatest common divisor. The largest number that divides both 2 and 3 evenly is 1. We check our subset S, which contains 1, 2, 3, and 30. Since the number 1 is safely inside our subset, the meet condition passes for this pair without any issues. However, a sublattice must satisfy both conditions, so we must now check the join operation. Moving to the join operation, we must find the least common multiple for 2 and 3. The smallest number that both 2 and 3 can multiply into is 6. Now we look at our subset S, which only contains 1, 2, 3, and 30. The number 6 is completely missing from our subset. Because the join operation produced a result that does not exist inside S, the subset is not closed. Physically, this means the structure breaks down, and we conclude it is absolutely not a sublattice. To truly understand this failure, let us look at the Hussey diagram for the divisors of 30. You can clearly see the elements 1, 2, 3, and 30 highlighted in blue. These form our subset. While the elements 2 and 3 are safely inside, tracing their paths upward to find their join leads directly to the number 6. Notice the red arrows converging on 6, which is crossed out because it is left out in the cold, outside our subset. This visual break in the structure is exactly what it means to fail the closure property. Now that we've seen the math, you might wonder why this matters. Understanding sublattices is incredibly important in real-world applications like computer science, specifically in database security and access control. Security clearances often form a massive lattice structure, ranging from public data at the bottom to top-secret data at the top. If a specific group of users and files forms a valid sublattice, system administrators know for a mathematical fact that information flowing between these users will never accidentally leak to a higher or lower security tier outside their group. To wrap up our lesson, let us review the most important ideas. First, a sublattice is simply a self-sufficient subset of a larger lattice, acting as a perfect miniature version of the parent structure. Second, it must contain the results of all meet and join operations for its own elements. Finally, if any operation forces you to look outside the subset to find the answer, the subset is broken. You have now covered the full topic of sublattices and you know exactly how to test them.